All right, today I wanted to make a video about evaluating the sum of a geometric infinite series. So I'm going to talk about that and give you some context. So a geometric series is any series of the form, the sum, usually it starts from the index 0 to infinity, of some real number a multiplied by the multiplying factor r to the power of n. And the conditions to tell if this geometric series, is either convergent or divergent is as follows. So it only depends on r. If, I'll call this equal to s, if the absolute value of r, the multiplying factor, is less than 1, then the sum s is convergent, which means that everything adding together equals a specific number. And we actually have a formula for that when we're talking about an infinite geometric series, and that formula is s equals a over 1 minus r. And then the other way, if the absolute value of r is anything else greater than or equal to 1, then s is divergent. And if it's divergent, the sum doesn't equal a specific number. It kind of just never calms down. So we don't have a formula for that, and we just end there. Now we're going to get into a couple examples where we're finding if a sum s is convergent or divergent, and if it's convergent, we're going to be calculating its sum. So let's go. The example we're going to be working with is this sum 3 minus 1 plus 1 over 3 minus 1 over 9 plus 1 over 20, 7, and so on. And we want to find if the sum is convergent or divergent. And if it's convergent, we're going to find what it evaluates to. So I'm going to call this sum equal to s. And you know what? Just for fun, I'm going to rewrite this sum in the formula like this. So right now, I can say that this is equal to the sum. Let's start the index from 0. N equals 0 to infinity, because 0 index is just fine to work with. And then I'm going to find my a value that we were talking about before. And so we want it in the form a multiplied by r to the power of n. And because n is starting from 0, the very first term is going to have that r to the power of 0, which is just 1. So then we're just left with a multiplied by 1 as our first term. So that a is equal to 3, our first term. So a is actually equal to 3. And then what's our multiplying factor? R is the multiplying factor. So how do I get from 3 to minus 1? Well, I can multiply by negative 1 over 3. So I'm going to put that as my R value. Minus 1 over 3 to the power of n. And you can actually write this out term by term, and you'll get this thing up here. Now, we're going to see if this is convergent or divergent. So my R value is equal to negative 1 over 3. So the absolute value of r equals 1 over 3. And because this absolute value of r is less than 1, we can say that s is convergent from the conditions that I mentioned at the beginning of the video. And if it's convergent, that means that the sum is going to evaluate to a specific number when we have infinitely many terms. And the formula for that is s equals a over 1 minus r. What is a? A was just 3, because this is equal to n equals 0 to infinity of a multiplied by rn. So you just kind of match things. 3 is the a, and then r is negative 1 over 3. So we have 3 over 1 minus r is negative 1 over 3. This is going to be 3 over 1 minus minus plus 1 over 3. 3 over 1 plus 1/3 is 4 over 3. And then we can turn this into a multiplication by flipping the denominator. 3 over 4. So this sum equals 9 over 4 when we add the infinite terms together. Let's go to another example. So the second example I'm going to be doing is s, the sum, is equal to the geometric series starting index as n equals 1, and on the numerator we have minus 6 to the power of n minus 1, and then on the denominator we have 5 to the power of n minus 1. So usually when we're talking about geometric series, I mentioned how you have the sum of a multiplied by r to the power of n when we had the index as 0. But here we have the power of n minus 1. So that's kind of an issue. We can't really do anything yet. But let's see if we can do some shifting of the index, which we're allowed to do because an index is just called a dummy variable, and we're allowed to switch things around a little bit. So for my very first term, if I plug in n equal to 1 into the exponent, I get the exponent of 0, which is the same thing we had if we had a r to the power of n with the index 0. So we're allowed to do some shifting, and it works like this. So this is equal to n equals 0. I'm doing what's called shifting the index, and then I can rewrite this. Now the index is 0, and here when I plugged in 1 for my first term, I got the power of 0 because 1 minus 1 is 0. So now that the index is 0, I can write the power as n because I still need that exponent for the first term to be 0. So it's going to go like this: minus 6 to the power of n over 5 to the power of n. Now we have an exponent of n on the top and the bottom. So we can pull that n outside of the bracket, and we're going to get a form that we like to see. Factor the n out, I get minus 6 over 5 to the power of n. Now this is in the geometric series form that we like it to be in. We have a, which is actually 1, multiplied by r to the power of n. So we're going to say that r is equal to the number that's inside of the exponent. So r is equal to negative 6 over 5. And then the absolute value of r is equal to 6 over 5. And then going back to the conditions I stated at the beginning of the video again, the absolute value of r is 6 over 5. 6 over 5 is greater than or equal to 1. So that means s, the sum, must be divergent. Thus, s is divergent. If it's divergent, we have to do no other work because s doesn't evaluate to a specific number when we add everything together. One more quick example before I end the video for today. We're going to be working with the sum s is equal to the sum of 5 multiplied by negative 1 over 3 to the power of n minus 1 again. We don't like that power to the n minus 1. We want it to be n. And we're starting from the index 0. So we can't do any shifting here like the last example because we had n equals 1 and then we had an exponent of n minus 1. So the first term has an exponent of 0 already, which is what the geometric series format looks like. However, I'm going to start writing some terms out for this series, and we're going to notice a pattern here. So the first term is when n equals 0, it's going to be 5 multiplied by negative 1 over 3. 0 is n, so as 0 minus 1, exponent is going to be minus 1. So that's the first term, plus the second term. Now n is equal to 1 because we're summing up to infinity. And so the exponent is going to be 1 minus 1 is 0. Next term, 5 multiplied by negative 1 over 3 to the power of 1. Next term, 5 negative 1 over 3 to the power of 2, and so on. Now, I want to notice something about this. This starting term here has the exponent of 0, and then it goes 1, 2. So actually, I can rewrite this as follows. Keep the first term the same, minus 1, plus I can put this in the form of a geometric series now, because the exponent starts from 0. So what I can say is a, the number in front, is always 5, so that's our a value, multiplied by r, which is just whatever's inside the exponent, negative 1 over 3 to the power of n. And because here n is the exponent and the exponent starts at 0, our index starts at 0 now. N equals 0 to infinity. And this is a geometric form. So we can work with this. We know inside here the negative 1 over 3 is our r value. So the absolute value of r is 1 over 3, and 1 over 3 is less than 1. So this part right here must be convergent. So let's find out what this sums up to. It's just going to be the formula a over 1 minus r once again. So the a value is 5, which goes on top. And then we have 1 minus r. R is negative 1 over 3. And then we still have this annoying first term over here. So I'll just rewrite that. Now, do you see how it's going to be a real number now? So this series is actually convergent. So I have a negative 1 exponent. That means I flip the fraction. So I get negative 5 multiplied by 3. It's going to give me minus 15. Plus 5 over 1 minus 1 over 3 is going to be 4 over 3 on the denominator. And then we flip that fraction. So it's going to be 5 multiplied by 3 over 4 gives me 15 over 4. Do a little bit of simplifying. Minus 15 plus 15 over 4, what's that going to be? Well, I can change the minus 15 into the minus 60 over 4, add 15 over 4 to that, I get minus 45 over 4. So that is what this sum evaluates to. So those were some tricky algebraic, silly questions that we solved, and they could pop up on an exam or, in an assignment or whatever. So I hope that helps.